In this lesson, we're going to talk about various separation axioms related to topological spaces. At the end of the previous lesson, recall that we restricted our focus to topological spaces with a certain type of base, i.e. topologies with a countable base. The property of second countability, in other words, having a countable base, effectively requires that a topological space does not have too many open sets. The properties considered in this lesson require that a topological space does not have too few open sets. The reason for this requirement is that topologies with too few open sets tend to provide little information since their structure is overly simple. The extreme example is the indiscrete topology, which we talked about before, where we have only the entire set X and the empty set as being open sets. A bit of a warning, the term separable is used in the previous lesson, and the terms separation and separated in this lesson have different meanings. And not my idea, but it's just how things are defined in the mathematical literature, so I'm going to go along with the standard definitions. On this slide, I'm going to state some preliminary definitions, and on the following slide, I want to give a list of axioms which I've taken from the Wikipedia article Separation Axiom. The axioms are listed with a letter like T1, T2, so forth. It comes from the German word Trennung Axiom, which means separation axiom. And that's the standard notation that's used. So let's start. First, let me reiterate, I guess I should say, the definition of a neighborhood, because that's going to be used here. I have it, I believe I talked about it in lesson 14, so you don't need to page back to that. I have it listed here. So a subset Y of a topological space is a neighborhood of a point X in our topological space X if there's an open set U where U is in Y and then U contains the point X. So you may recall that. We're going to need that for some of these definitions. So the first definition is 2 points of a topological space are called or considered topologically indistinguishable if they have exactly the same neighborhoods. And 2 points are topologically distinguishable if they are not topologically indistinguishable. So I have an example here. X could have a neighborhood that does not include Y, but every neighborhood of Y could include X. In this case, X and Y would be topologically distinguishable. Okay, so that's one preliminary definition. The other preliminary definition is this concept of separated. And again, I warned about this not being the same as the way the term separable was used in the previous lesson. So in a topological space X, points X and Y are separated if each of them has a neighborhood that is not a neighborhood of the other, i.e. neither belongs to the closure of the other. Two subsets A and B of X are separated if each is disjoint from the other's closure though the closure themselves do not have to be disjoint. So they could kind of just intersect just at the boundary, but they wouldn't. They would be otherwise disjoint. Suppose A and B are subspaces of topological space X. A and B are said to be separated if each is disjoint from the closure of the other. Okay, so these are our preliminary definitions. We're going to use these in these separation axioms, these T1, T2, so forth, on the next slide. And then the slide after that, I'll show you some diagrams, which I think will help visualize what we're talking about here. On this slide, we have the separation axioms. I'm going to read through these. I know it's a lot to take in. You may want to just pause the video once I get done reading these and then kind of study it a bit. And then on the next slide, I have diagrams for a few of these, which may help you visualize a little bit. Although I would suggest doing some two-dimensional Venn diagram like drawings on your own to kind of convince you that each one of these is different. So let's start with the first one, T0 or Kolmogorov. A topological space that has this property: if any two distinct points in X are topologically distinguishable, and a topological space X is T1 or accessible or Fouché, if any 2 points in X are separated. A topological space is Hausdorff or T2 or separated, if any 2 distinct points in X are separated by disjoint neighborhoods. Every Hausdorff space is also T1. The Hausdorff property is designed to make limits of sequences unique. A topological space is regular if any point and any closed set F in X, but not containing X, are separated by neighborhoods. A topological space X is regular Hausdorff, or T3, if it is T0 and regular. A topological space is normal if any 2 disjoint closed subsets of X are separated by neighborhoods. And a topological space X is normal Hausdorff, or T4, if it is T1 and normal. So I'll pause here to give you a chance to pause the video. And as I say, you may want to just study this a bit and draw some diagrams on your own to kind of visualize the differences. And I'll show you at least a few of these, some exemplary diagrams in the next slide for a few of these. We have a few examples here, sort of high-level diagrams, I guess you would call them. And they exhibit Hausdorff, regular, and normal. The E and F in these diagrams are closed sets. X and Y are points, and these light gray areas are neighborhoods. So each one of these squiggly things is a neighborhood. And just to summarize from the previous slide, T4 implies T3, implies T2, implies T1. And I've copied the definitions of each here, so you don't need to switch back and forth. You can just look at those as I explain the different examples. So Hausdorff or T2 are separated if any 2 distinct points are separated by distinct neighborhoods. So I show that here. We have a neighborhood around X and a neighborhood about Y, and they're disjoint. So this would have to be true for any 2 distinct points in our space to be Hausdorff. And that's a very common property. You'll see this a lot in math books related to real analysis and complex analysis. They'll just say Hausdorff and sometimes not even define it. If it's an advanced book, they'll just assume you know what this is. So it's an important concept to know, and it's not that hard. You can see here it's what it means. Regular is if any point X and any closed set F in X, but not containing X, are separated by neighborhoods. And the implication here is disjoint. I left out the word disjoint, but I should have added that in here. So you see an example here. So we have a closed set F and a point X, and there's a neighborhood around X and a neighborhood around F that's disjoint and separates the two. So that's regular. And then just going up one more level of complexity, or a little bit stronger than this previous condition. Normal is if any 2 disjoint closed subsets of X are separated by, again, a disjoint neighborhood. So we have here E and F, and there's a neighborhood about E and a neighborhood about F that are disjoint. Okay, so those are the examples, and these are three of the more common ones that are used in various mathematical theorems. The following theorem gives us another way to characterize T1 spaces. A topological space X is T1 if and only if each of its points are closed sets. Let's go in the forward direction. Assume X is a T1 space and take any X in our topological space. For every Y not equal to X, there exists an open set U sub Y such that Y is an element of U sub Y and X is not an element of U sub Y. And that comes from these two definitions, which I've copied from a previous slide, so you don't need to flip back and forth. Then U equals the union of all these U sub Y's is open, being the union of open sets. So the complement of X equals U is open, and thus the singleton set X is closed. Now we can go in the other direction, assume that every point is a closed set. Take 2 points, X and Y. So that would mean these singleton sets, X and Y, are closed subsets of X. Then U equals the complement of X is an open set containing Y but not X. And V equals the complement of Y is an open set containing X but not Y. And that fits our definition of a T1 space. So we have this theorem which may be helpful in identifying whether or not a space is T1. Every metric space is a T4 space. And if you recall from the definitions earlier, which I copied down here, T4 implies your T1 and normal. And we have a theorem 102, which we just proved concerning T1. We'll use that. And then normal means that any two disjoint closed subsets of X are separated by neighborhoods. So we'll prove that second in this paragraph, and then going on to the second slide. So assume X is our given metric space. Since each point X can be represented as the intersection of all closed subsets, the closure of the open balls of radius R about X, each point in X is a closed set, and thus X is T1 space by theorem 102, which we just went through. Now for the other condition concerning normality, take any two disjoint closed sets E and F and X. For each X in E, there exists some radius R sub X greater than 0 such that the open ball centered at X with radius R sub X intersected with F is empty. And similarly, for each Y in F, there exists a radius R sub Y greater than 0, such that the open ball centered at Y of radius R sub Y intersected with E is an empty set. And then we define these two sets here. We take the union of all the open balls that we defined for points in E, but we take the radius divided by 2, and then we take the union of all the open balls that we defined for the points Y and F, and again we divide the radius by 2. We're going to combine things, that's why we're dividing these radii by 2. And it follows that E is a subset of this union, and F is a subset of this union here. In other words, F is a subset of V. And what we need to show is that U and V are disjoint in order to disjoint neighborhoods in order to prove the normality principle. So we'll do that on the next slide. To complete the proof, we need to show that U and V are disjoint. To that end, we take some Z in the intersection of U and V, and then we derive a contradiction, thereby showing that U and V have an intersection that's empty. In other words, they're disjoint. So if there's a z in U intersection V, this implies there's some x in and y in F such that the distance between x and z is less than r sub x over 2, and the distance between y and z is less than r sub y over 2. Then we use the triangle inequality here on the distance between x and y. We get this. Then we just plug in these two results here. So we get the distance between x and y is less than or equal to the max of r sub x, r sub y. If r sub x is greater than r sub y, then y is in the open ball about x of radius r sub x. And if r sub x is less than r sub y, then x is in the open ball centered at y with radius r sub y. Either way, we have a contradiction, and so the intersection of U and V must be empty. Uri-Son's lemma is the topic of this slide. We first need to define something called a Uri-Son function. Subsets A and B of a topological space are said to be separated by a continuous function if there exists a continuous function f from x, which is our topological space, into the unit interval 0, 1, the real numbers here from 0 to 1, such that f of A equals 0 for every A in A and f of B equals 1 for every B in B, all the while f being continuous. Any such function is called a Uri-Son function for A and B, and in this case A and B are necessarily disjoint. And for normal topological spaces, we have the following theorem concerning subsets of a topological space that are separated by a continuous function. So here we have it. Uri-Son's lemma, topological space X is normal if and only if for any two non-empty closed subsets A and B of X, so that's for any two, there exists a continuous map F from X into the unit interval such that f of A equals 0 for every A in A, and f of B equals 1 for every B in B. In other words, there exists a Uri-Son function for A and B. And if you're interested in proof, just go to Wikipedia and look up Uri-Son's lemma, and they'll have a sketch of a proof there. Uri-Son's lemma is used in the proof of Uri-Son's metrization theorem, which gives criteria for a topological space to be metrizable. And this theorem is as follows. Every second countable regular Hausdorff space is metrizable. Remember, second countable was the condition that the base that was countable, that we had a countable base for our topological space. And regular and Hausdorff we just defined a few slides ago. You may want to page back to that just to refresh your memory. But if these conditions hold, then the space is metrizable. The proof is a bit long and complex, but I'll give you a reference here. Theorem 34.1 in the book by Moncrief, reference 81 in my book, which you can download and look up the reference. And also, I believe Moncrief's book is available for borrowing from the Internet Archive, so you can borrow that for, I think, an hour at a time. Again, if you're interested in the proof. Okay, so that's it for this lesson. We have a few more topics to cover under topology, and I'll get to those in the next lesson.